Okay, so today we're going to talk about the seismic inversion methods. At least the methods which I know, I did have few more, but I haven't put in all of them. But at least 3 or 4 we will cover as the inversion methods and why we do inversion and like what the history of it. And so, which applies to which area. I got use. Seeing the screen, yeah? Okay. Your screen sharing. I don't see.
Yeah, we can see the screen.
Okay, that's good. Okay, so let's, yeah, so inversion, it would be covering the inversion methods in the, yeah, I can't move the slide. So today's talk, like deterministic, stochastic, Bayesian, hit cube, and neural networks, various inversion methods and how they are getting along with each other. And then we will have next week automation in quantitative sequence stratigraphy, then deep learning in geoscience application, mainly deep learning from the open detect point of view. Then we'll have the rock physics, pre-stack modeling, and a simultaneous inversion workflow to come back and we'll finish up, and then we'll have the series again some other time. But this makes it eight talks. So we will cover, as usual, our services, Petro-Explorers, then theory of seismic inversion, simultaneous inversion, discrete neural networks, and then stochastic and hit cube inversion, various stochastic types, and just concluding. And so that would be the workflow. Just starting with our services as a reservoir characterization. Now it's been 12th year of providing these services in various aspects, either whole going through the pre-stack side or the post-stack inversions, quantitative interpretation, using the true amplitude processing, getting into the neural networks and more, which we specialize in neural networks, which plus means now deep learning is coming as a part of it. So, and then on geology side, we cover a lot, again, Valentina, and cover a lot on sequence stratigraphy and going back to petrophysics, rock physics, and anesthesia, working on log analysis, even developing stuff, and coming into the seismic sequence stratigraphy, combining it together into the final, again, neural networks based analysis to finalize. So these are our kind of whole cover what we could or should do, could or can do for the clients. So they worked all over the North America, of course, Canada, and then US, going down to Colombia, quite a bit of work. We have a partnership now developing in overall South America as well. So, and then Mexico. So, and on the Asian and African side, South Asia covering India and Pakistan and some Oman. And then in Africa, a lot of rift basins and there was like one carbon sequestration project in with JNOC as well as in North Sea, some of the well work and mass well work in North Sea. So software side, we have been since the beginning, we have been Open Detect's representative in Canada, and we've worked a lot of tools of Open Detect with inversions and sequence stratigraphy and a lot of plugins. So we work with Chimney analysis and others. We work with them as well as we work by ourselves and sell the software. This is what we are developing, and again, anesthesia is part of it is development of the quantitative stratigraphy workflow. Which is going to automate the stratigraphy or quantitative stratigraphy from the well data up to the. So next week we will cover as a whole that area, and Hampson Russell for inversions and AVO has been our base tools, including petrophysics is GS software for the tool. So that is the software base. In OpenDetect, there is a geoscience package, which is as a whole covers nearly everything what DGB plugins that include many of the neural network, deep learning, Synthrock, and so whole workflow which anyone have would have it with these plugins. It's like a complete geoscience package or geoscience workbench, you can call it. So now I'm going to start with the case kind of work with the case study, the manual, one of the lower manual estuary, like channel sands, which are coming in, filling in the estuary. It's more like was a system like present day. Indus is here, so it's by the side of Indus, one of the estuary. You can clearly see a lot of channels coming in and then come into bay and overall into the open ocean. And same as with the Indus River. So that's kind of what wide area was there in the old estuary system. So it's very important even for the inversion to understand the geology and what kind of geological system because of the model needed for geological system. So looking at the data again, the old Blackfoot data, that you get the channels into the Mississippian, cut down into Mississippian carbonates as a estuary, and then filled up layer by layer over the lower manual top of the estuary, and then various coal layers on the top in upper manual. So that is kind of a stack of being very very familiar with many of the Albertan exploration teams, that in order to then separate and which one are oil filled, gas filled, and what are the attributes of the rocks, because you can easily get problem with due to the frequency being low, you can get into a lot of trouble with where which channel is going, because they are cross-cutting so many channels on top of each other. So if you look at the model, which you have the upper lithic channel, upper channel, lower channel, but you cannot really tell lithic channel to be different from the background. Like you could see the some of the what called the lithic channel. It's just anything channel which is didn't it may be silty channel, but again, channel can be filled by silt, sand, shale, anything. So you cannot call something a channel just by channel that it is sand filled, and that's the problem with most of these where you need inversion in order to get down to which one are the channel, like which are sand filled, where it's shale filled, where it's tight, maybe may or may not be reservoir, may have porosity, may not have porosity. So looking at general like AVO response, it is there. The AVO response of course you have to do a lot of massaging of the gathers to make condition the gathers, but once you have conditioned the gather, you can see the class 3 AVO, and you can see the background kind of event, which is a regular background event or close to background. That would be still a sand in the lower sand, but it is not fully class 3. So depending on the first interface, so it's a reflection based. So once you have reflection, then your reflection attributes are there, but not all sands will respond depending on their thickness and those. So, and there could be very false anomalies there with the change, like look like class 2, but it may not be. So when we look at the scaled Poisson's ratio, looking at the gathers, you can see the AVO response of class 3, and that is responding right from this channel as well as this channel, doing a very strong cross plot in the cross plot domain. So, but what is this? In order to differentiate, separate these with the second white speck related and various other changes in the amplitude with offset. you need to understand the geology, what is the backgrounds on each of these sections, and what is the geology. We can clean up those by doing a more conditioning, and then once you clean up, that would be like narrow down to two specific. So this area where you can differentiate the red, where you can differentiate it from the background. So that was the AVO of that. Now, jumping from AVO to inversion, that is when you need from interface attributes to the interval attributes. So that is what inversion does. So going back to Roy Lentzeth in 1977 and his paper in 1979, various tools came up. That was the idea was to how to get rid of the wavelet in order to, from a general wedge model, if you have a wavelet with the side lobes, it is really difficult to tell that if it is a wedge, where is the wedge, and is it the unconformity on the top, and then the wedge finishes here, or where the tuning. So once you change into colors the older way, then you start seeing the tuning, and that tuning, if you can remove the wavelet or deconvolve with the from wavelet, that is what the process called inversion. But if you see, there is still there will be side lobes, and there will be some effect of the inversion residual. But that is it's showing what the inversion would be. And again, the tuning at certain points, the inversion would stop working because you cannot have the amplitude. It is really inverting the amplitude through sparse spike. That was the first one, was sparse spike. So you put a spikes and then adjust the spikes till you get a real model which would match. So Roy Lentzeth again is published paper in 1979, and that's quite interesting to see this now, like with the Swan Hills, like Swan Hill Reef, with the porosity, what he could predict the porosity of this white. He was talking about this white layer of the porosity on the top of the Swan Hills, and how get invert these. I would love to build this color palette, but it is done by hand and done by contouring. So contouring of the like hand contoured. So maybe computer will not have exactly same value because it's generalized by the hand contouring. But you come up with the idea of the getting the sonic logs at every location, and that was post-stack inversion. So that really goes to the theory of inversion, as that Earth model consists of the real Earth and the input wavelet, and it creates this seismic. But when you have recorded seismic, if you have estimated it well, the wavelet, then you should be able to get back the Earth model. But again, because of the band limited, these are not unique. Earth model would not be of this much high frequency. It would be a lower frequency Earth model. But again, that is the point from this. But it not only the wavelet, because we lose the lower frequencies, we may not be able to get the exact Earth model. So that is where it comes. We need backgrounds. So two important things: we need wavelets and we need backgrounds. And so that's where I jump up to simultaneous inversion, although there were many stages before the simultaneous inversion came up. So in 2000, simultaneous inversion started, actually based on the elastic inversion. So the elastic inversion by Patrick Connolly was in 1999. He published the paper of the elastic inversion, which mean at every angle you could find the impedance at various angles. And he was joining the intercept and gradient to make at different angle, it was called the chi angle. So from that chi angle, we could take that concept and put it together, that if you have the angle gathers, and you can actually invert it simultaneously, all the angle gathers, then you can combine as a combined solution that would be called simultaneous inversion. So it would be all of the amplitude variation is put in as together, and then there is a ZP-ZS relation, which is impedance of log-log relation between P and S impedance, and log-log relation between P and P impedance and density. So if you take that relationship, and if you simultaneously invert for PS and density, their relationships will allow it to be more scalable. So it actually solved the scaling problem. The other problem it solved was the that wavelet would be changing with offsets or changing with angle. So you can actually estimate more than one wavelets at different angles. So that makes the compensate for any frequency or amplitude variation, which usually we're supposed to fix in the gathers, but this will allow a more flexible way to get it into the results. So results are much balanced, much easier to reflect than individually doing P and S inversion separately, and density was very hard to gain, and it's still with simultaneous inversion density is not that good, but VPVS ratios and those become much better behaved in the simultaneous inversion. So important parts of simultaneous, again, as I said, the wavelet extraction from various near, mid, far. You can have 3 wavelets or 5 wavelets, depending on how much variation you have, because some of the near to far variation could be just related to frequency. They may not be related to any other. So the frequency tuning at different angles would be different, and that makes the elastic model that it's not really different, or it's not real AVO if it is a background based on frequency. So that becomes very important to extract frequencies at different wavelength. First, also I have to make sure the polarity is correct, and that is done a lot of work based on the wells to get the polarity right. Then, as I said before, the ZP-ZS relationship and ZP and density relationships are based on the wells. You can have one or more wells and apply the trends so that those trends will be honored when it is trying to scale between. So they have various regression coefficients which would be used to scale the inversion results. So they are more interpretable and come into the other domains. They can be more representative of the real rock physics. Next step is going through just doing the inversion analysis. And a major problem in this area is like the logs usually terminate at the interface of the Devonian or Mississippian carbonates interface, and that becomes really difficult to get the model across. So sometimes you have to add a model and going below. So there are various things you can do, but the results are pretty sustainable except the few of the coal interfaces and multiples generated due to coals. So those are need to be addressed in the gathers, like in the conditioning of the gathers. So I would say that that inversion results more than half dependent on how the gathers are processed. So how the data is processed and how good the gather conditioning is. So we do conditioning part as well. So it is allow the various multiples and those to be removed, because many of the false AVO anomalies were really either normal multiples or converted wave multiples. So which converted wave multiples are even more complex than the normal multiples. So once you have that, then you have the background. Background could be very low frequency, and backgrounds are usually, depending on in the linear sparse spike inversion, you would not honor it. You can do a colored inversion, then add the background. But usually in simultaneous inversion, you have a very low frequency background, which is not covered by seismic. So then you really pay attention to the residual. So residual is the one which would be telling you how much is the how much is not being inverted. So yeah, if you look back in the residual here, you would see that what percentage and where are the things where the problems are. Of course, these are highly conditioned gathered so that you don't see the problem as a dipping reflectors, but you do see some energy at the Mississippian level and those. So that is the some of the best practices come in to look at the residuals and make sure you have the residual watching and go back to the processing and try to address those things what you see in the residual. But in addition to residual, you still have the problem. It's not a unique solution. Yeah. So the inversion is not a unique solution because you can have more than one solution to the same at the frequency range. You can have more than one solution in for the inversion with still doing the same thing. But once you have the P wave and S wave impedance, you can combine them together using the using from the concepts from the Lame's constant. It's really good to follow the Lame's compressional and shear velocity and have that relationship. What very nice paper by Bill Goodway about magic of Lame. We follow that in our most of the work. So it is really impressive to come how it is related to the geology, especially rigidity and those. So it was in like deep basin. We did a lot of related make your own template kind of thing. For each area, there could be a slightly difference in the template depending on the pressures and like depth of burial pressures and various other things. So it could be different from different. So you have to create the yardsticks as you go from the different areas. So now if I look at the logs from the same logs, you will run the lambda rho mu rho and look at the cross plots of various logs. So which area are really the oil bearing or sands are in which part, and then wet sands are in which area. So the blue would be considered wet sand, and while tight sands and then carbonates and others in different areas. So you can build a template of that. And once that template with the porosity and these changes, you can start seeing that you could actually sort out those lithologies from the others using these. So, but now it is only two-dimensional template where you can see the one well and then try to scale the seismic to that and then transfer that template to the seismic. And you can do a facies interpretation based on these. So that is one way of doing, but again, it is based on deterministic inversion. So in the deterministic inversion, you can come up with the facies where your sands, shales, and like various other zones are the lithology zones, and you can separate and start doing your estuary to figure out what was going on within the estuary. But now the one important part when it comes to the deterministic inversion, that it is a middle ground, like it is the best solution, but it is an average solution. So it is not really necessarily the best exact solution. So especially the higher frequencies, because if you add higher frequencies from the wells, then you are pushing your own information into your model, which makes it kind of, you are putting your answer so that you see the answer which you already imagined. So a priori information becomes a very a problem. So that is where neural networks inversion, from my point of view, it's like neural network inversion come in after the deterministic inversion or various elastic inversion as an input. So that then you can relate to a larger number of wells the neural network way of putting that, finding that relationship and then applying that learning to the rest of the hidden layers. So you have to have at least quite a few wells as a training set, and then a few wells as the test set, which mean at least 20%. Like if you have 8 well as a training, 2 wells as a testing, and then you can predict better within a 3D. So that would be the neural network inversion. It is, from my point of view, a little bit more robust than the stochastic, because you're not putting your statistical information, you're still taking information from the seismic as your main information, as a correlation to the high frequency between low frequency. So wells have high frequency and inversion have lower frequency, but it matches to come up with the inversion. But parameters, the input, either you go with the reflectivity data only directly, like old way of doing neural network inversion, or you work with the color inversion or elastic and other model-based inversions to work together. So that would be this was one like very example from South Asia. Like there are very difficult to predict the porosities and those, but the inversion was actually quite noisier. But with the neural network, quite few wells, you could actually figure out the areas of the high porosity, and also this is carbonates at the base, clastic wedge on the top, and a very structurally affected with the normal faults. And then you can start looking at the facies relationship. That is a straight lines relationship between them. So yes, further deterministic can be further enhanced with neural network inversion. So then the whole school of comes in of stochastic inversion. So stochastic inversion have its roots in reservoir simulation, like because there's a lot more. So inversion is a more interaction between a geophysicist and a geologist, or between geophysicist and a reservoir engineer. So getting that connection between these two, the deterministic is usually your LMR, and those bases is good for the geologist to go back and forth between the rock types. But for detailed grid or the work, you need kind of statistical solution, or statistical mean the wells you need to anyway, the geological model need to simulate the porosities and those things. So this have a more continuity based on the variograms than actually what is coming from the seismic, because seismic could, if you're working with neural network inversion, the seismic could have gaps, and you could have other things which would not be interpolated because you based on the seismic and noisy trace. But in the stochastic, you're already starting with a model and populating the model with finding the relationship between the actual well data relationship and the seismic data. So that one becomes the background in order to stochastic. So stochastic wise, you can go then make that relationship as a background relationship, and then simulate to find as many solutions possible. Depending on the iterations, you come in the 10 best possible solutions. So that is how stochastic would work. We'll go over this Cardium study. That in Cardium, there was this one sand layer, so like various upper sands and main sands are are in a shore face setting with a lot of sand. Some are mainly they are this edge where they are oil filled and gas filled, while further up there are wet as well. And but mostly it is to predict the sands, the distribution of the sands based on the stochastic inversion. So the this sums up the slide is how a stochastic inversion run in a smaller portion, how the various amplitude effect is provide a corridor of the range, the gray range, where you are close enough to the real value. So there would be many models which could lead to these traces. So when the log models, again, this is post-stack only. So the many models which would lead to the various traces then can make that, predict that model. So each model representing a trace which are close enough. So you create the inversion and then create a synthetic from that inversion, and they are between changes in the models would not affect, or changes in the log distribution would not affect the resultant peaks or troughs. So that is where the differentiation, how much range you have. So within that range, and also again variogram, you give the background variogram, which well, how much effect of each well to the rest of the seismic data, how they are related. You fit a variogram to this, and also create. So you cannot really get to every sample attribute. So that's where stochastic inversions usually deal with the facies models, like those of facies of various facies of the sandy facies, shaly facies, different type of shales with a high impedance, low impedance. So impedance versus gamma ray can give you those PDF clusters. So probability density functions, which can separate these. So facies can be separated on probability density functions, uh, can be separated on P-wave impedance, S-wave impedance, and various attributes, plus their porosity and those sand. So sand, type of sand, if the high impedance sand, low impedance sand could be different in their rock types. So that is the, or some have carbonate matrix, some have other non-carbonate. So that comes then to simulation. So you have a Gaussian or various other simulation types to come up with using the variogram to see how the distribution, where the possibility of having more green. We are running on a very small interval in this case. So stochastic inversion usually focuses in a reservoir zones much smaller areas than the deterministic, which you're running over whole of the seismic for some time, like on a larger interval. But then you're refining with the stochastic interval. So when you run, then there are probabilities, and this is the shale probability, like a lot harder in the a lot more shale probability in these reds, well, sands like Valley River sands and other sands. And then you can slice through those, and then this is the sand probability, which would have the shore face coming down. You have a higher sand probability here as well as you come through, and you can start seeing the trends of the shore face trends within this zone as it comes through various sand and shaly facies. So then you can take out the P90, P50, or P10 probabilities. So lowest sand probability is where you're seeing these yellow, whereas the P90 probability, or least probable sand, which mean that you have optimistic and pessimistic point of view all all at the same time while distribution. So if you sum up all the stochastic inversion results or average, that would be your deterministic inversion. So that is the relation between the stochastic and deterministic. Stochastic is done deterministic over a big range, like so range of possible probabilities and taking the highest results from those iterations. So that leads us into the last or main is the hit cube stochastic inversion. So it is a newer method, and well, newer, it's about in last 10 years, but it's been applied. So the hit cube inversion is you building a rock property models in a much detail. So you're building the synthetics for um, every possible scenario, like a wet versus gas versus oil, as well as sand versus shale. All these within a smaller interval, you're building all kind of model details, and then creating a pseudo synthetic and pseudo wells, which mean you don't necessarily need wells right on the 3D. You need in the area, you need to know the geology very well, and you predict based on the range of the geology. So you come with the so seismic volume is tied to the model traces, like correlated with the model traces, and then you find what is called based on correlation and shift. You can find with a time shift and correlation, you can find the best match for best model for each seismic trace, which mean you have, if you have enough like thousands of models with variation, you can find the best five more model which match that trace, and then take the average of those models, and that would give you that trace. So it's a trace by trace inversion, which is allows you to take every trace to be represented by the properties which are built in the pseudo wells. It's quite a strong way. And this is the newest method also applied in Odyssey, which is the probability using elastic inversion by Pat Connolly. Recently, he have presented as well uh, to use the similar method of taking the log data and creating a synthetics. And this is what normally what interpreters would do, is to take the synthetic or various variation and then put it the various variation, create the synthetic, and then go through your line and see which one matches. But again, computer can do a better job than what we can do by hand, taking all the synthetic and trying to tie the everything, including amplitude, which is not on the synthetic, your time interval. So taking the, again, drilled wells, taking the rock physics, creating the PDF for probability density functions, creating properties for each interval, and distribution as well, geological distribution, if it's uh, sand shale layering, thin sand layering, or is it what kind of geology? It's a coarsening upward single sand unit, or is it a layered shale and sand, or it's carbonate layers inside, like ostracot zone or other carbonate zones could come in. So based on that, you can build the whole stratigraphic framework, and that's what we will bring in the QStrat stuff into this because you will already have a built model. So in the manual group, you can say the Collie layers on the top, like three coals, and the G1 is the glauconite, and then taking the Mississippi. So each interval, you can give it a different variation in thicknesses, what you see in the maximum and minimum thicknesses. Even you can do a little bit more addition to it, and then various property differences. So as you change the properties, you can have, like now, this is your model going in with the various variations, and that would be synthetic associated to each model. And you can have a pre-stack, like in a different offset synthetics, the same way. So each of the input data which you want to deal with, you have to generate synthetics related to that. And also then you also come with if you're using inversion, uh, deterministic inversion as an input, you can actually use that as well. Or you can use the lambda rho mu rho volumes as a input. And so uh, and then what it does find the delta t, like the change differences in the time difference between synthetic to seismic, like how, because you're controlled by the horizons, so that would give you the adjustment. So it's able to adjust the similar to the neural network inversion does, is that allow to flexibility, because you're not exactly on your interpretation may not be exactly tying with the inversion unless you have interpreted on the inversion data. So the result is like this, the same your uh, estuary is getting, like you would get a very high and low score depending on did you get a good match with the one of the model or you did not get a good match. So in this area where on the shoulder of the estuary, you're not getting a good correlation, you're getting about 60. It means I need to do a better job in defining those shoulder geology and putting in my synthetic models, or I need to do a better imaging job where it may have multiples in those and which not image properly. But this gives you a again your uncertainty or your uh, error bars are all as a volume, so you know the score and the volume of the error. So how much is good inversion versus the bad inversion within the interval is selected. So looking at the estuary again of the Mississippian estuary with various channels trying to fill in. The mostly it's muddy and those zones, except a few very prolific channels. So what you see is like a porosity or the sand porosity right now is just showing between 22 and 28, but various porous channel system depending on the slice as we take the various slices, how it is this is the density inversion of the density. So you can always take various combination of attributes like but each of the attributes is how they are correlated back. So you can have right now I'm just showing the wrongly, but it is AVO, like intercept and gradient would have their own intercept and gradient synthetic, so the tie would be a different based on the same wavelet, but it would be the tie between A and B. So you have various combination of attributes we can use, and up to 5 in this case of HitCube. So HitCube inversion, again summing up the that it can give you a more precise going into the more details and separating out the probability of the sands and shales within this. So it is an alternative to stochastic. So HitCube is the result. It is similar to, you know, if you use LMR as an input and then HitCube based, you can define those facies before and then use that to invert the facies. So the idea is not to interval, either you interval properties as the continuous properties or as a facies properties, or interval like a facies, which is a combination of many ranges, like it's like a cutoff range. This same way, it's like if your porosity is between 10 and 15%, that would be a one facies, then 15 to 25% or high porosity versus middle porosity. So the main is the inversion allowed us to see beyond the wavelet, it is a different interpretation. So it need to be done interpretation on the inversion, because you want to see especially it is important when you don't have a overwhelming AVO response and you have too much mixed lithology going through. So you need, other than the interfaces, you need to do the inversion and convert it into a real rock properties like the V-shale, V-dolomite, or halite or anhydrite, various separating each of the lithology and giving it, narrowing it down or building in the models. So a lot of advancement in the theory and application over many decades, and it continues till today. We have an inversion session, and we're looking forward to more papers coming in this session. So many are now pointing toward the probability and stochastic based direct phase inversion. Again, it doesn't take away the point that gathers need to be conditioned and all those. So the most hard work goes into the processing and gather conditioning and those. But the JIFI, like joint inversion of phases and impedance, that is one thing which came up. Odyssey, which is BP's leading, like Pat Connolly is leading this Odyssey group by Seagal and Blueback, and the Bayesian linear inversion out of Brazil recently coming up with the probability directly using deterministic inversion with various elastic deterministic and elastic deterministic inversion, and then HitCube. We do a kind of work in HitCube with DGB. And so many tools in the industry. I cannot know of all of them, but we try to know and go through the inversion thing. So the idea was to sum up these inversion tools and tell us or remind ourselves where we are and where we have to go, which one works better for one idea or the other. And deep neural networks, which is the deep learning, have a lot of promises. We will cover the deep learning in a couple of weeks, and then we see the inversion applications of the deep learning. It's the same way as I see as neural network application. It is a kind of neural network on a steroids. So it's a deeper layers. Does it have a lot of promises to come up with the results. Sorry. Thank you, and I would any questions and discussion we would love to have. We have time.